In mathematics, the logarithm is the inverse operation to exponentiation. That means the logarithm of a number is the exponent to which another fixed value, the base, must be raised to produce that number. In simple cases, the logarithm counts repeated multiplication. For example, the base 10 logarithm of 1000 is 3, as 10 to the power 3 is 1000. The multiplication is repeated 3 times. More generally, exponentiation allows any positive real number to be raised to any real power, always producing a positive result. So the logarithm can be calculated for any two positive real numbers b and x where b is not equal to 1. The logarithm of x to base b, denoted log(b), is the unique real number y such that by equals x. For example, as 64 equals 26. We have log 2 equals 6. The logarithm to base 10 is called the common logarithm and has many applications in science and engineering. The natural logarithm has the number e as its base. Its use is widespread in mathematics and physics, because of its simpler derivative. The binary logarithm uses base 2 and is commonly used in computer science. Logarithms were introduced by John Napier in the early 17th century as a means to simplify calculations. They were rapidly adopted by navigators, scientists, engineers, and others to perform computations more easily. Using slide rules and logarithm tables, tedious multi-digit multiplication steps can be replaced by table lookups and simpler addition because of the fact, important in its own right, that the logarithm of a product is the sum of the logarithms of the factors, provided that b, x and y are all positive and b1. The present-day notion of logarithms comes from Leonhard Euler, who connected them to the exponential function in the 18th century. Logarithmic scales reduce wide-ranging quantities to tiny scopes. For example, the decibel is a unit quantifying signal power log ratios and amplitude log ratios. In chemistry, pH is a logarithmic measure for the acidity of an aqueous solution. Logarithms are commonplace in scientific formulae, and in measurements of the complexity of algorithms and of geometric objects called fractals. They describe musical intervals, appear in formulas counting prime numbers, inform some models in psychophysics, and can aid in forensic accounting. In the same way as the logarithm reverses exponentiation, the complex logarithm is the inverse function of the exponential function applied to complex numbers. The discrete logarithm is another variant. It has uses in public key cryptography, motivation and definition. The idea of logarithms is to reverse the operation of exponentiation, that is, raising a number to a power. For example, the third power of 2 is 8, because 8 is the product of three factors of 2. It follows that the logarithm of 8 with respect to base 2 is 3, so log 2 8 equals 3. Exponentiation, the third power of some number b, is the product of three factors of b. More generally, raising b to the nth power, where n is a natural number, is done by multiplying n factors of b. The nth power of b is written bn, so that exponentiation may be extended to by, where b is a positive number and the exponent y is any real number. For example, b-1 is the reciprocal of b, that is, 1, b. Definition: the logarithm of a positive real number x with respect to base b, a positive real number not equal to 1, is the exponent by which b must be raised to yield x. In other words, the logarithm of x to base b is the solution y to the equation. The logarithm is denoted log(b). In the equation y equals log(b), the value y is the answer to the question, to what power must b be raised, in order to yield x. This question can also be addressed for complex numbers, which is done in section complex logarithm, and this answer is much more extensively investigated in the page for the complex logarithm. Examples: for example, log 2 equals 4, since 24 equals 2 times 2 times 2 times 2 equals 16. Logarithms can also be negative. Since a third example, log 10 is approximately 2.176, which lies between 2 and 3, just as 150 lies between 102 equals 100 and 103 equals 1000. Finally, for any base b, log b equals 1 and log b equals 0, since b1 equals b and b0 equals 1, respectively. Logarithmic identities. Several important formulas, sometimes called logarithmic identities or log laws, relate logarithms to one another. Product, quotient, power and root. The logarithm of a product is the sum of the logarithms of the numbers being multiplied. The logarithm of the ratio of two numbers is the difference of the logarithms. The logarithm of the pth power of a number is p times the logarithm of the number itself. The logarithm of 8 pth root is the logarithm of the number divided by p. The following table lists these identities with examples. Each of the identities can be derived after substitution of the logarithm definitions or in the left-hand sides. Change of base. The logarithm log b can be computed from the logarithms of x and b with respect to an arbitrary base k using the following formula. Typical scientific calculators calculate the logarithms to bases 10 and e. Logarithms with respect to any base b can be determined using either of these two logarithms by the previous formula. Given a number x and its logarithm log b to an unknown base b, the base is given by particular bases. Among all choices for the base, 3 are particularly common. These are b equals 10, b equals e, and b equals 2. In mathematical analysis, the logarithm to base e is widespread because of its particular analytical properties explained below. On the other hand, base 10 logarithms are easy to use for manual calculations in the decimal number system. Thus, log 10 is related to the number of decimal digits of a positive integer x. The number of digits is the smallest integer strictly bigger than log 10. For example, log 10 is approximately 3.15. The next integer is 4, which is the number of digits of 1430. Both the natural logarithm and the logarithm to base 2 are used in information theory, corresponding to the use of nats or bits as the fundamental units of information, respectively. Binary logarithms are also used in computer science, where the binary system is ubiquitous, in music theory, where a pitch ratio of 2 is ubiquitous and the cent is the binary logarithm of the ratio between two adjacent equally tempered pitches, and in photography to measure exposure values. The following table lists common notations for logarithms to these bases and the fields where they are used. Many disciplines write log instead of log b, when the intended base can be determined from the context. The notation blog also occurs. The ISO notation column lists designations suggested by the International Organization for Standardization. History. The history of logarithm in 17th century Europe is the discovery of a new function that extended the realm of analysis beyond the scope of algebraic methods. The method of logarithms was publicly propounded by John Napier in 1614, in a book titled Mirifici Logarithmorum Canonized Scripture. The common logarithm of a number is the index of that power of 10 which equals the number. Speaking of a number as requiring so many figures is a rough allusion to common logarithm, and was referred to by Archimedes as the order of a number. The first real logarithms were heuristic methods to turn multiplication into addition, thus facilitating rapid computation. Some of these methods use tables derived from trigonometric identities. Such methods are called prostaphiaresis. Invention of the function now known as natural logarithm began as an attempt to perform a quadrature of a rectangular hyperbola by Grégoire de Saint Vincent, a Belgian Jesuit residing in Prague. Archimedes had written the quadrature of the parabola in the 3rd century BC, but a quadrature for the hyperbola eluded all efforts until St. Vincent published his results in 1647. The relation that the logarithm provides between a geometric progression in its argument and an arithmetic progression of values prompted A. de Sarasar to make the connection of St. Vincent's quadrature and the tradition of logarithms in prostaphyresis, leading to the term hyperbolic logarithm, a synonym for natural logarithm. Soon the new function was appreciated by Christian Huygens, Batavia, and James Gregory. The notation log y was adopted by Leibniz in 1675, and the next year he connected it to the integral logarithm tables, slide rules, and historical applications. By simplifying difficult calculations, logarithms contributed to the advance of science, and especially of astronomy. They were critical to advances in surveying, celestial navigation, and other domains. Pierre-Simon Laplace called logarithms an admirable artifice which, by reducing to a few days the labor of many months, doubles the life of the astronomer, and spares him the errors and disgust inseparable from long calculations, a key tool that enabled the practical use of logarithms before calculators and computers was the Table of Logarithms. The first such table was compiled by Henri Briggs in 1617, immediately after Napier's invention. Subsequently, tables with increasing scope were written. These tables listed the values of log b and bx for any number x in a certain range, at a certain precision, for a certain base b. For example, Briggs' first table contained the common logarithms of all integers in the range 1–1000, with a precision of 14 digits. As the function f equals bx is the inverse function of log b, it has been called the anti-logarithm. The product and quotient of two positive numbers c and d were routinely calculated as the sum and difference of their logarithms. The product CD or quotient CD came from looking up the anti-logarithm of the sum or difference, also via the same table, and for manual calculations that demand any appreciable precision, performing the lookups of the two logarithms, calculating their sum or difference, and looking up the anti-logarithm is much faster than performing the multiplication by earlier methods such as prostaphyresis, which relies on trigonometric identities. Calculations of powers and roots are reduced to multiplications or divisions and lookups by, and many logarithm tables give logarithms by separately, providing the characteristic and mantissa of x. That is to say, the integer part and the fractional part of log 10. The characteristic of 10x is 1 plus the characteristic of x, and their significance are the same. This extends the scope of logarithm tables. Given a table listing log 10 for all integers x ranging from 1 to 1000, the logarithm of 3542 is approximated by greater accuracy can be obtained by interpolation. Another critical application was the slide rule, a pair of logarithmically divided scales used for calculation, as illustrated here. The non-sliding logarithmic scale, Gunter's rule, was invented shortly after Napier's invention. William Orchard enhanced it to create the slide rule, a pair of logarithmic scales movable with respect to each other. Numbers are placed on sliding scales at distances proportional to the differences between their logarithms. Sliding the upper scale appropriately amounts to mechanically adding logarithms. For example, adding the distance from 1 to 2 on the lower scale to the distance from 1 to 3 on the upper scale yields a product of 6, which is read off at the lower part. The slide rule was an essential calculating tool for engineers and scientists until the 1970s, because it allows, at the expense of precision, much faster computation than techniques based on tables. Analytic properties. A deeper study of logarithms requires the concept of a function. A function is a rule that, given one number, produces another number. An example is the function producing the xth power of b from any real number x, where the base b is a fixed number. This function is written logarithmic function to justify the definition of logarithms. It is necessary to show that the equation has a solution x and that this solution is unique, provided that y is positive and that b is positive and unequal to 1. A proof of that fact requires the intermediate value theorem from elementary calculus. This theorem states that a continuous function that produces two values m and n also produces any value that lies between m and n. A function is continuous if it does not jump, that is, if its graph can be drawn without lifting the pen. This property can be shown to hold for the function f equals bx. Because f takes arbitrarily large and arbitrarily small positive values, any number y greater than 0 lies between f and f for suitable x0 and x1. Hence, the intermediate value theorem ensures that the equation f equals y has a solution. Moreover, there is only one solution to this equation, because the function f is strictly increasing, or strictly decreasing. The unique solution x is the logarithm of y to base b, logb. The function that assigns to y its logarithm is called Logarithm Function or Logarithmic Function. The function logb is essentially characterized by the above product formula. More precisely, the logarithm to any base b greater than 1 is the only increasing function f from the positive rails to the rails satisfying f equals 1. An inverse function. The formula for the logarithm of a power says in particular that for any number x, in prose, taking the xth power of b and then the base b logarithm gives back x. Conversely, given the positive number y, the formula says that first taking the logarithm and then exponentiating gives back y. Thus, the two possible ways of combining logarithms and exponentiation give back the original number. Therefore, the logarithm to base b is the inverse function of f equals bx. Inverse functions are closely related to the original functions. Their graphs correspond to each other upon exchanging the x and the y coordinates, as shown at the right. A point on the graph of f yields a point on the graph of the logarithm and vice versa. As a consequence, logb diverges to infinity if x grows to infinity, provided that b is greater than 1. In that case, logb is an increasing function. For b less than 1, logb tends to minus infinity instead. When x approaches 0, logb goes to minus infinity for b greater than 1. Derivative and antiderivative analytic properties of functions pass to their inverses. Thus, as f equals bx is a continuous and differentiable function, so is logb. Roughly, a continuous function is differentiable if its graph has no sharp corners. Moreover, as the derivative of f evaluates to ln bx by the properties of the exponential function, the chain rule implies that the derivative of logb is given by, that is, the slope of the tangent touching the graph of the base b logarithm at the point equals 1. The derivative of ln is 1x. This implies that ln is the unique antiderivative of 1x that has the value 0 for ex equals 1. This is this very simple formula that motivated to qualify as natural, the natural logarithm. This is also one of the main reasons of the importance of the constant t. The derivative with a generalized functional argument f is the quotient at the right-hand side is called the logarithmic derivative of f. Computing f by means of the derivative of ln is known as logarithmic differentiation. The antiderivative of the natural logarithm ln is related formulas, such as antiderivatives of logarithms to other bases, can be derived from this equation using the change of bases. Integral representation of the natural logarithm. The natural logarithm of t equals the integral of 1 x dx from 1 to t. In other words, lane equals the area between the x-axis and the graph of the function 1, x, ranging from x equals 1 to x equals t. This is a consequence of the fundamental theorem of calculus and the fact that derivative of lane is 1, x. The right-hand side of this equation can serve as a definition of the natural logarithm. Product and power logarithm formulas can be derived from this definition. For example, the product formula lane equals lane plus lane is deduced as the equality splits the integral into two parts, while the equality is a change of variable. In the illustration below, the splitting corresponds to dividing the area into the yellow and blue parts. Rescaling the left-hand blue area vertically by the factor t and shrinking it by the same factor horizontally does not change its size. Moving it appropriately, the area fits the graph of the function f equals 1, x again. Therefore, the left-hand blue area, which is the integral of f from t to 2, is the same as the integral from 1 to u. This justifies the equality with a more geometric proof. The power formula lane equals r lane may be derived in a similar way. The second equality uses a change of variables, w equals x1, r. The sum over the reciprocals of natural numbers is called the harmonic series. It is closely tied to the natural logarithm. As n tends to infinity, the difference converges to a number known as the Euler-Mastroianni constant. This relation aids in analyzing the performance of algorithms such as quicksort. There is also another integral representation of the logarithm that is useful in some situations. This can be verified by showing that it has the same value at x equals 1, and the same derivative. Transcendence of the logarithm. Real numbers that are not algebraic are called transcendental, for example, pioneer, such numbers, but is not. Almost all real numbers are transcendental. The logarithm is an example of a transcendental function. The Gelfond-Schneider theorem asserts that logarithms usually take transcendental, i.e., difficult, values.